Hello friends, nice meeting you. We are meeting through this media in which we shall be discussing certain things connected with advanced econometric subject. In this lecture series, we have designed 12 lectures which will be taken up one by one. Before going to that, let me introduce something about the subject econometrics. Econometrics means economic measurement. This subject is composed of three main branches: economics, mathematics and statistics. Economic theories get their applications through these three subjects, and they have immense applications, immense usefulness everywhere. By studying this subject, there can be number of theories which are used in economic models can be tested and applied at many places. In this lecture, first of all, we will give you certain preliminary things about econometric subject. Then we will give you the fundamental basis on which it is built up, that is classical 2 variables model and classical 3 variables models. By learning this in nutshell, you will be able to have a fundamental basis of the subject econometrics, and I am sure that this will lead to the milestone where we want to go. Please remember that this is our pursuit for perfection. So, let us start our lecture.
Hello friends, today we are going to discuss preview of econometrics methods. Lesson 1. What is econometrics? The word econometrics means economic measurement. As per Goldberger, econometrics may be defined as the social science in which the tools of economic theory, mathematical and statistical inference are applied to the analysis of economic phenomena. Thale described it as the subject which is concerned with the empirical determination of economic laws. In a way, it is an economist approach to statistical analysis. It can be considered as a field based upon a theoretical quantitative and empirical quantitative approach to economic problems. Thus, econometricians are regarded as applied economists using the tools developed by theoretical econometricians to examine and analyze economic phenomena, while applying different tools and techniques to understand the behavior of the variables concerned for any economic phenomena. Everything is based upon what is called data analysis. In general, we have three possible types of data. Number 1, cross-sectional data. This type of data consists of measurements for individual observations, persons, households, firms, states, countries, etc. For example, population census figures for India in 2001 and 2011 and so on. Number 2, time series data. This type of data consists of one or more variables such as GDP, interest rates, unemployment rates, etc. over time in a given space like a specific country or state or industry, etc. For example, production data for steel industry during last 30 years in India. Number 3, panel or longitudinal data. It consists of a time series for each cross-sectional unit in the sample. This data contain measurements for individual observations, persons, households, firms, states, countries, etc. over a period of time, days, months, quarters, years. For example, data for 4 companies about their investments, value of the firm and capital stock during last 20 years. Traditional or classical econometric methodology consists of the following steps. Number 1, theoretical statement or hypothesis. Number 2, to specify the mathematical model of the theory. Number 3, to specify the statistical or econometric model. Number 4, to collect data. Number 5, to estimate the parameters of the model. Number 6, to state and test the hypothesis. Number 7, to obtain prediction based upon the fitted model. Number 8, to use the model developed for its policy implications. Econometrics may be divided into two broad categories, A. Theoretical and B. Applied. In each category, the subject can be approached by classical or Bayesian tradition. We want to consider for our study here the classical approach. Number 2, classical two variables regression model. We illustrate this by means of family weekly consumption and income data. Let y equal to weekly consumption in monthly units and x equal to weekly income in monthly units. Since consumption depends upon income, we may post a linear model as under: y equal to alpha plus beta into x plus u. We denote it as equation number 1, where alpha and beta are the parameter of the model and u is the disturbance term. If we collect information about the whole population, for example a region or state, the above equation 1 is called population regression function, PRS. Instead, if we draw a sample from the population, then we can write the above relation as in equation 2, which is called sample regression function, SRF, and it is given by y equal to alpha cap plus beta cap multiplied by x plus e. We denote it as equation number 2, where alpha cap and beta cap are the estimated values for alpha and beta and e is the error term. This estimate of alpha and beta are obtained by the method of least squares. Hence, they are called OLS estimators, ordinary least square estimators. This is done by least square methods. Analytically, yi equal to alpha cap plus beta cap multiplied by xi plus ei, where I equal to 1, 2 up to n. We denote it as equation number 3. Then ei equal to yi minus alpha cap minus beta cap multiplied by xi equal to error. Hence, summation 1 to n ei square equal to summation 1 to n yi minus alpha cap minus beta cap multiplied by xi whole square, which is equal to error sum of squares, and we denote it as equation number 4. We find alpha cap and beta cap by minimizing the error sum of squares. Diagrammatically, we are searching for a line in the plotted graph for xi yi such that the sum of squares of the distance from the points to the line is minimum. Theoretically, we can obtain OLS estimators by the formula beta cap equal to summation 1 to n xi yi divided by summation 1 to n xi square. We denote it as equation number 5, and alpha cap equal to y bar minus beta cap multiplied by x bar. We denote it as equation number 6, where xi equal to capital Xi minus x bar and yi equal to capital Yi minus y bar, where x bar equal to mean of x and y bar equal to mean of y. If we insert these estimators in the model, then the prediction for yi for given xi can be obtained as yi cap equal to alpha cap plus beta cap multiplied by xi, where I equal to 1, 2, 3 up to n. The formula for variances and standard errors of the estimators are variance of beta cap equal to sigma cap square whole divided by summation 1 to n xi square. We denote it as equation number 7. Variance of alpha cap equal to summation xi square divided by n multiplied by summation xi square whole multiplied by sigma cap square. We denote this equation by equation number 8, where sigma square is population variance and it is estimated by sigma cap square equal to summation 1 to n ei square by n by 2, and we denote it as equation number 9, where ei equal to yi minus yi cap, I equal to 1, 2 up to n. Positive square root of the estimated parameters are their standard errors. Thus, standard error of beta cap equal to positive square root of variance beta cap. We denote it as equation number 10, and standard error of alpha cap equal to positive square root of variance alpha cap. We denote it as equation number 11. The correlation coefficient between x and y is computed from the formula R equal to summation xi yi whole divided by under root of summation xi square multiplied by summation yi square, where xi equal to xi minus x bar and yi equal to yi minus y bar. We denote it as equation number 12. Theoretically, R lies between -1 to 1. So, we can write -1 less than or equal to R less than or equal to 1. R square, usually denoted by capital R square, is called coefficient of determination. R square lies between 0 and 1. Values of R square near to 1 indicates very strong linear relation between the concerned variables. For example, R square equal to 0.87 shows that about 87% of the variation is explained by the model, thus leaving only 13% which is not explained. If R square equal to 1, it is a perfect positive correlation between x and y. Here all the points will fall on the fitted line. If R square equal to 0, there is no linear relationship. However, there may be some sort of non-linear relationship. Testing the model. A. Testing the parameters. We can use student's t-test as test for beta, null hypothesis h naught, beta equal to beta 0, where beta 0 equal to specified value of beta versus alternative hypothesis beta not equal to beta 0. Then the test statistic t equal to beta cap minus beta 0 whole divided by standard error of beta cap. We denote it as equation number 13, which has student's t distribution with n minus 2 degrees of freedom. We can compare the calculated value Tc with tabulated value Tt from t table for n minus 2 degrees of freedom and decide if t calculated greater than t tabulated, we reject null hypothesis and significant. If t calculated less than or equal to t tabulated, we may accept null hypothesis not significant. We can test at 5% or 1% level of significance. If the hypothesis may be accepted, then we have confidence interval for beta given as beta 0 minus t alpha by 2 multiplied by standard error of beta cap less than or equal to beta less than or equal to beta 0 plus t alpha by 2 standard error of beta cap. We denote it as equation number 14. This gives the interval in which beta will fall with probability 1 minus alpha for given beta 0. So, for example, alpha equal to 0.05 gives 95% confidence interval for beta cap and alpha 0.01 gives 99% confidence interval for beta cap. 2. Test for alpha. Null hypothesis alpha equal to alpha 0 versus alternative hypothesis alpha not equal to alpha 0, where alpha 0 specified value of alpha. Then t equal to alpha cap minus alpha 0 whole divided by standard error of alpha cap. We denote it as equation number 15, which has student's t distribution with n minus 2 degrees of freedom. Then the decision can be taken as above. Here also we get the confidence interval for alpha as alpha 0 minus t alpha by 2 multiplied by standard error of alpha cap less than or equal to alpha less than or equal to alpha 0 plus t alpha by 2 multiplied by standard error of alpha cap, and we denote it as equation number 16. Hence, as usual, we get 95% and 99% confidence interval as shown before. Number 3. Test for raw. We put hypothesis, null hypothesis, raw equal to 0 versus alternative hypothesis raw not equal to 0, where raw is the population correlation coefficient. Then apply t-test by T equal to R multiplied by under root of n minus 2 whole divided by under root of 1 minus R square. We denote it as equation number 17, which has students T distribution with n minus 2 degrees of freedom. For suitability of the model, we expect T to be significant. Number 4, test for sigma square. We put hypothesis, null hypothesis sigma square equal to sigma 0 square versus alternative hypothesis sigma square not equal to sigma 0 square, where sigma 0 square is specified value of sigma square. Then we apply chi-square test by the formula chi-square equal to n minus 2 multiplied by sigma cap square whole divided by sigma 0 square with n minus 2 degrees of freedom, and we denote this formula by equation 18. If chi-square calculated is less than or equal to chi-square tabulated, we may accept the null hypothesis. If chi-square calculated is greater than chi-square tabulated, we reject null hypothesis. 100 into 1 minus alpha % confidence interval for sigma square is given by n minus 2 multiplied by sigma cap square divided by chi-square alpha by 2 less than or equal to sigma square less than or equal to n minus 2 multiplied by sigma cap square divided by chi-square 1 minus alpha by 2. We denote it as equation number 19. Chi-square alpha by 2 and chi-square 1 minus alpha by 2 are the tabulated values for chi-square for significance level 100 multiplied by 1 minus alpha %. For example, for 95% confidence limits, chi-square alpha by 2 equal to chi-square 0.025 and chi-square 1 minus alpha by 2 equal to chi-square 0.975. Number 5. Testing the model. For appropriateness of the model, we can carry out analysis of variance, which is ANOVA, as given in the following table. Here f equal to a dash divided by b dash, which is equal to error sum of square divided by 1 whole divided by residual sum of square divided by n minus 2, which has f distribution with degrees of freedom nu1 equal to 1 and nu2 equal to n minus 2 degrees of freedom. We expect f to be significant for deciding about the suitability of the model. Thus, if f calculated is greater than f tabulated, f is significant, and if f calculated is less than or equal to f tabulated, f is not significant. ANOVA also determines for significance of R square. Note: number 1. The above discussed classical two variables linear regression model is based upon the following assumption. Number 1. Expected u equal to 0. Number 2. Variance of u equal to sigma square. Number 3. Disturbance term u has normal distribution. This is needed for the testing of hypothesis problems. Number 2. The given model assumed linear relationship can be tested for normality assumption by means of test for normality. Number 3. For hypothesis testing, the decisions can also be taken by means of p-values. P-value is the lowest significance level at which a null hypothesis can be rejected. Number 4. Once linear model is posed between the variables concerned, note that these are causal variables, sum cause for relationship. Only estimation process is not sufficient. Hypothesis testing part must be done as indicated above. Number 5. Also, model will be useful if prediction are given based upon the fitted model. This can also help for policy planning decisions. Number 6. In the above model, alpha is the intercept and beta is interpreted as the marginal propensity to consume MPC, beta is the slope coefficient. Number 7. Standard error of a statistic is defined as the positive square root of the sampling variance of the statistic. Number 8. We have two measures, s square equal to 1 by n summation 1 to n xi minus x bar whole square and small s square equal to 1 by n minus 1 summation 1 to n xi minus x bar whole square. Small s square is unbiased estimator for sigma square. That means expected s square equal to sigma square. Thus, n minus 1 multiplied by small s square equal to n multiplied by s square, which gives s square equal to n upon n minus 1 whole multiplied by s square. Illustration. Example 1. The following data give the advertising expenditure and sales of a company during year 1990 to 1997. Estimate linear regression model for sales on advertising expenditure and estimate sales when the advertising expenditure is 60,000 rupees. We consider the model y equal to alpha plus beta multiplied by x plus u, where x equal to advertising expenditure in thousand, y equal to sales in millions rupees, y cap equal to alpha cap plus beta cap multiplied by x. Using relation beta cap equal to summation 1 to n xi yi divided by summation 1 to n xi square, where xi equal to xi minus x bar and yi equal to yi minus y bar, we get the value of beta cap equal to 0.125 and then alpha cap equal to y bar minus beta cap multiplied by x bar. By using the value of beta cap, we get alpha cap equal to 3.87. Hence, the estimated linear regression is y cap equal to 3.87 plus 0.125x. Now, when x equal to 60, y cap equal to 3.87 plus 0.125 multiplied by 60 and we get the answer 11.37. Hence, the estimated sales will be 11.37 million rupees. Example number 2. Following is the consumption income relationship for 10 families. Interpret this model. Here, alpha cap equal to 12.35 and beta cap equal to 0.46, which is equal to MPC. Standard error of alpha cap equal to 3.95 and standard error of beta cap equal to 0.87. For an increase in income level by 1 unit, more than 46% of the income goes into consumption. 78.54% of the variation is explained by the model. Now, let us understand another model, trivariate linear regression model. For an industrial setup in a region, let us define Cobb-Douglas production function as under: Q equal to A multiplied by L raised to alpha multiplied by K raised to beta, which is denoted by equation number 1, where Q equal to output, L equal to labor force participation and K equal to capital invested. Alpha and beta are the partial elasticities of labor and capital respectively. We can write double log model relationship from the above model, which is log Q equal to log A plus alpha multiplied by log L plus beta multiplied by log K plus U. We denote it as equation number 2 and define yi equal to beta 1 plus beta 2 multiplied by x2i plus beta 3 multiplied by x3i plus ui. We denote it as equation number 3, where yi equal to log qi, x2i equal to log li, x3i equal to log ki, beta 1 equal to log a, beta 2 equal to alpha and beta 3 equal to beta 3. For the above PRF based upon a sample of size n, SRF can be stated as yi equal to beta 1 cap plus beta 2 cap multiplied by x2i plus beta 3 cap multiplied by x3i plus ei. We denote it as equation number 4, where I equal to 1 to up to n. This is trivariate linear regression model as given in equation 4. Note that beta 1, beta 2, beta 3 are the partial regression coefficients and beta 1 cap, beta 2 cap, beta 3 cap are their estimated values. Using again least square principles, we can find OLS estimators by minimizing error sum of squares. Summation 1 to n ei square equal to summation yi minus beta 1 cap minus beta 2 cap x2 I minus beta 3 cap x3 I whole square. We denote it as equation number 5. Equation 3 is the equation for plane of regression for y on the variables x2 and x3. For the model in equation 3, we make the assumptions. Number 1. Expected ui given x2i, x3i equal to 0 for all I. Variance of ui equal to sigma square for all I, which is homoscedasticity. Number 3. Covariance of ui uj equal to 0, where I equal to 1 to up to n and j equal to 1 to up to n, where I not equal to j. Variables x2 and x3 are not linearly related, no multicollinearity. OLS estimators for beta 1, beta 2 and beta 3 are given by the relations as x2i equal to capital X2i minus x2 bar, which is equal to deviation from mean, x3i equal to capital X3i minus x3 bar, which is equal to deviation from mean, yi equal to yi minus y bar, which is equal to deviation from mean. Then we have the relations beta 2 cap equal to summation yi x2i multiplied by summation x3i square minus summation yi x3i multiplied by summation x2i x3i whole divided by summation x2i square multiplied by summation x3i square minus summation x2i x3i whole square. We denote it as equation number 6. Beta 3 cap equal to summation yi x3i multiplied by summation x2i square minus summation yi x2i multiplied by summation x2i x3i whole divided by summation x2i square multiplied by summation x3i square minus summation x2i x3i whole square. We denote it equation number 7. Then beta 1 cap is computed from beta 1 cap equal to y bar minus beta 2 cap multiplied by x2 bar minus beta 3 cap multiplied by x3 bar, which is equation number 8. Let us define R23, which is equal to correlation coefficient between x2 and x3 given in equation number 9. R23 square equal to summation x2i x3i whole square divided by summation x2i square multiplied by summation x3i square. We denote it as equation number 9. We have following relations for variance of estimators. Variance of beta 2 cap equal to sigma square whole divided by summation x2i square multiplied by 1 minus R23 square. We denote it as equation number 10. Variance of beta 3 cap equal to sigma square divided by summation x3i square multiplied by 1 minus R23 square. We denote it as equation number 11. Standard error of beta 2 cap and beta 3 cap are the positive square root of their variances and covariances between beta 2 cap and beta 3 cap is given by covariance of beta 2 cap beta 3 cap equal to minus R23 multiplied by sigma square whole divided by 1 minus R23 square multiplied by square root of x2i square multiplied by square root of summation x3i square, which is denoted by equation number 12. In the above formula, sigma square is estimated by sigma cap square equal to summation ei square divided by n minus 3. We denote it as equation number 13. Note that when the parameters beta 1 cap, beta 2 cap, beta 3 cap are estimated, the value of yi for given values of x2i and x3i can be estimated or predicted by yi cap equal to beta 1 cap plus beta 2 cap multiplied by x2i plus beta 3 cap multiplied by x3i, where I equal to 1 to 3 up to so on. We can define product moment simple correlation coefficient as under. Note that y implies 1, x2 implies 2, x3 implies 3. R12 equal to correlation coefficient between y and x2. R13 equal to correlation coefficient between y and x3. R23 equal to correlation coefficient between x2 and x3. Then We have the correlation coefficient matrix P, defining the correlation coefficient as given here. Where Rij equal to Rji, Ij equal to 1, 2 and 3, where I not equal to j, which is a real symmetric matrix. Number 2, partial correlation coefficients. We considered pairwise the correlation coefficient of two variables when the third one is kept constant. Then we can define the partial correlation coefficients as R12.3 equal to partial correlation coefficient between y and x2, keeping x3 as fixed constant. R13.2 equal to partial correlation coefficient between y and x3, keeping x2 as fixed constant. R23.1 equal to partial correlation coefficient between x2 and x3, keeping y as fixed constant. Variable after subscript shows omitted category. The relations for the above partial correlation coefficients are given in terms of the simple product movement correlation coefficients as R12.3 equal to R12 minus R13 multiplied by R23 whole divided by square root of 1 minus R13 square multiplied by 1 minus R23 square. We denote it as equation number 15. R23.1 equal to R13 minus R12 multiplied by R23 whole divided by square root of 1 minus R12 square multiplied by 1 minus R23 square. We denote it as equation number 16. R13.2 equal to R23 minus R12 multiplied by R13 whole divided by square root of 1 minus R12 square multiplied by 1 minus R13 square. We denote it as equation number 17. These are also called first order correlation coefficients. All product moment and partial correlation coefficients lie between -1 and +1. Number 3, multiple correlation coefficient and multiple coefficient of determination. To examine the combined effect of both x2 and x3 on the dependent variable y, we measure multiple correlation coefficient denoted by R1.23 or capital R. It is defined as R equal to R1.23 equal to correlation of y cap, which is equal to covariance of y cap whole divided by square root of variance of y multiplied by variance of y cap. We denoted it as equation number 18. We define R square, that means R square 1.23 as the multiple coefficient of determination, and it can be computed by R square equal to explained sum of squares divided by total sum of squares, which is equal to EV divided by TV. We denoted it as equation number 19. R square always lies between 0 and 1. So, 0 less than or equal to R square less than or equal to 1. For example, R square equal to 0.73 means 73% of the variation is explained by the model, thus leaving only 27% unexplained. For our 3 variables linear model, formula for R square is given by R square equal to beta 2 cap multiplied by summation yi x2i plus beta 3 cap summation yi x3i whole divided by summation yi square. We denote it as equation number 20. Diagram representing the situation for multiple correlation of x2 and x3 on y. R square, that is R square 1.23, can be expressed in terms of 0 order correlation coefficients by the formula R square 1.23 equal to R12 square plus R13 square minus 2 R12 R23 R13 whole divided by 1 minus R23 square. We denoted it as equation 21. Similarly, it can be expressed in terms of 0 order and first order correlation coefficients given by R square 1.23 equal to 1 minus R12 square multiplied by 1 minus R13.2 square. We denote it as equation number 22. Number 4, R square and adjusted R square. To compare two R square values, one must take into account the number of x variables present in the model. We have R square equal to ESS divided by TSS, which is equal to 1 minus residual sum of square divided by total sum of square, which equals to 1 minus summation EI square divided by summation YI square. We define adjusted R square given by R bar square, which is R square adjusted by R bar square equal to 1 minus summation EI square divided by n minus 3 whole divided by summation EI square by n minus 1. We denote it as equation number 23. It is called adjusted R square for degrees of freedom associated with the sum of squares. This is useful for comparing two regression models. In each of them, dependent variable is the same, but explanatory variables can be different. Here, n equal to number of observations, that is sample size, k equal to number of parameters in the model including the intercept term, which is equal to 3. Relation between R bar square and R square is given by R bar square equal to 1 minus n minus 1 divided by n minus k multiplied by 1 minus R square. We denote it as equation number 24. Number 1. For k greater than 1, R bar square less than R square. Number 2. R square is positive but R bar square can be negative and its value is taken as 0. Number 3. We can choose model with greater R bar square as more suitable model. Number 5. Testing problems. Test procedures for ordinary and first order partial correlation coefficients are similar to those for two variables. Note that degrees of freedom equal to n minus 3. Also, confidence intervals can be computed accordingly. Number 6. ANOVA approach. For testing the suitability of the model, we have ANOVA table as shown in the slide. To test the hypothesis, null hypothesis beta 2 equal to beta 3 equal to 0 versus the alternative hypothesis beta 2 not equal to beta 3 not equal to 0. We expect f to be significant for validity of the model. Here f equal to a dash divided by b dash has f distribution with nu1 equal to 2 and nu2 equal to n minus 3 degrees of freedom. Hence, it can be tested as usual. 7. Testing for significance of R square. Null hypothesis rho square equal to 0, which implies rho equal to 0 versus alternative hypothesis rho square not equal to 0, which implies rho equal to 0. Rho is population multiple coefficient of determination. We have f equal to R square by 2 divided by 1 minus R square by n minus 3, which has nu1 equal to 2 and nu2 equal to n minus 3 degrees of freedom, and we expect f to be significant for validity of the model, that is for significance of R square. Note, only estimation of parameter is not sufficient. Number 2. One must go for testing problems as indicated above. Number 3. Once the model is found to be suitable, best fitted, we can obtain prediction of y based upon given or forecasted values of the explanatory variables. Number 4. This prediction can be useful for future planning purpose. Thank you.